In this video, we're going to talk about how we can determine the domain and vertical asymptotes of rational functions from the symbolic representation. So a lot of times we see rational functions or any function being written in the symbolic way of representation, where it's just an expression and we want to determine what's the domain restriction and vertical asymptotes. And really these two quantities go hand in hand with rational functions. So for the domain restriction of a rational function, just like any fraction we have this experience that we don't want the denominator to be a 0 for a fraction. And for the same argument, we don't want the denominator of a rational function to be 0 either. And that's going to give us a domain restriction. And graphically, what happens at that domain restriction is we're going to have the two sides of the function approaching either infinity or negative infinity, and thus create a vertical asymptote a lot of times in these domain restrictions. And that's what we are going to consider when we consider the vertical asymptotes. So it's going to be easier to start with a domain restriction and think about how these domain restrictions affect the result of vertical asymptotes. So looking at part A first, we have k of x equal to this expression. As we said, for the domain restriction, the only thing we need to make sure is denominator doesn't equal to 0. So if I want to identify the domain, I want x minus 10 doesn't equal to 0. To solve it, we can add 10 and get x doesn't equal to 10. And that's going to be the domain over here. From here, you can write the domain in interval notation or set builder notation. So we can say in set builder notation, the domain is x such that x doesn't equal to 10 over here. And in interval notation, we can say it's negative infinity to 10 union 10 to infinity over here. And using this information, if we want to consider the vertical asymptote over here, because that's the only domain restriction and we can't really simplify the function any further, we would say that the vertical asymptote in this case is x equals 10, because this is going to be this dashed line we saw in rational function graph where we can't have any function defined through that point over here. And now moving on to the next one, we have f of x. Again, we start off with a domain restriction that comes from the denominator doesn't equal to 0. And here we don't have a linear function. Whenever we have a quadratic equation to solve, we want to think about whether we can factor it and simplify from there. So if we want to factor that, we can use a GCF of x. Factor x out gives us x times x plus 2 doesn't equal to 0. And that's where all the factoring we learned before comes in really handy. And here, if we have the product doesn't equal to 0, we have either x doesn't equal to 0 or x plus 2 doesn't equal to 0. Actually, we should say and, because otherwise we would have one of them being 0 would result in the product being 0. So we want neither to be 0 in this case. And x doesn't equal to 0 is already solved for, and we also want x not equal to negative 2 over here. So as a result, we would want to say the domain is x such that x doesn't equal to 0 and x doesn't equal to negative 2. And in the interval notation, we can also say that we're going from negative infinity to negative 2, because if we go from the negative side, we'll hit negative 2 before we hit 0. And then negative 2 to 0, and then 0 to infinity. That's going to be our domain. Lastly, for the vertical asymptote, again, that we can't simplify this expression anymore, so we can say that the vertical asymptote is going to be x equals 0 and x equals negative 2. In this case, we have two vertical asymptotes. Now moving on to part C, we again start with the denominator part over here, and we would get x squared minus 3x minus 40 doesn't equal to 0. Again, it's quadratic, so we want to think about factoring or any method we have learned about solving quadratic equations, except we have it doesn't equal to 0. And if you look for the factoring, you should find x minus 8 times x plus 5 is going to be the result of what we're going to have in this case. And we got these two numbers because 8 times negative 5 is equal to negative 40, and 5 times negative 8 is negative 40, and also 5 plus negative 8 is negative 3. So these are the two numbers we want. And we want this doesn't equal to 0. So as a result, we get x minus 8 doesn't equal to 0, and x plus 5 doesn't equal to 0. So remember, when we're solving equations, we just want one of them to be 0 for the product to be 0. So if we want the product to be not 0, we need both of them to be non-zero values. And that's why we change the or. The negation becomes and over here. And therefore, we get x doesn't equal to 8 and x doesn't equal to negative 5. Therefore, the domain gets us to be, I'm going to use interval notation here, negative infinity to negative 5 first, and then negative 5 to 8, union 8 to infinity as a result. And therefore, for the vertical asymptote, we would get x is equal to negative 5 and x equals 8. So again, we have two vertical asymptotes. This happens when the denominator can be factored into a product of two factors and there's no simplification. Now for part D, when we have this, again we start off setting the denominator x squared plus 16 doesn't equal to 0. And if you don't recognize that right away, I hope you recognize it when you subtract 16 on both sides and see x squared is equal to negative 16. When this happens, we said x squared has to be non-negative. So if this negative 16 is less than 0 over here, we know this is impossible to have a real solution over here. So we can say there's no real solution for this, or a real number solution is what we really mean by no real solution. And by this case, we would say because of that, there's no domain restriction, or the domain can be all real numbers. So the domain can be all real numbers. You can use a fancy looking R to represent the set of all real numbers, or you can use the interval notation for negative infinity to positive infinity. Therefore, for vertical asymptote, because we don't have any domain restrictions, we can hit any value, then we would say there's none over here.